Hello, my name is Benjamin Eltzner, and I will speak about testing for uniqueness of estimators. First, I will introduce the notion of non-unique descriptors we use here, where we will speak about M-Estimators with a data space Q, a manifold descriptor space P, and a continuous estimating function rho, which maps an element from P and an element from Q to the positive real numbers. And we define the population, sample, and bootstrap Fréchet functions as the expected value of rho over the data space or the mean of rho over the data respectively. And the descriptors will then be global minimizers of these functions. Here we assume a finite number M of population descriptors, where the sample descriptors and bootstrap descriptors will still typically be unique in this setting. And for this reason, we also define local sample descriptors as the local minimizers of the sample Fréchet function near the population descriptors. Let's look at a simple example first, namely the Fréchet mean for a density on the circle. The descriptor space and the data space are both S1, and the function rho is the square distance. We look at a density with two modes, which are antipodal here and of the same size. And this on the right-hand side is the unwrapped representation where we assume periodic boundary conditions here. Now, the Fréchet function of this population is given by the black dotted line here, and we see it has two minima, namely a plus pi half and minus pi half. And we take samples of size 100 from this population, and we see that some of the samples will have their sample mean near plus pi half and only a local sample mean near minus pi half. And some of the samples, like the blue and purple one, will have their sample means near minus pi half. So if we want to do a t-test now, comparing the mean of the red sample with the mean of the blue sample, we will find that since the means are very far apart at a large enough sample size, the t-test will reject, but it shouldn't because they are both samples from the same population. And this is the problem we want to solve here. For this, we propose a hypothesis test for non-uniqueness, where the idea of this hypothesis test is to use the bootstrap. If we take bootstrap samples for this blue sample, for example, most of them will have the bootstrap mean near the sample mean. But some of them will have the mean actually near plus pi half, so near the local minimum of the sample Fréchet function. So we will get two clusters of bootstrap means, one near the sample mean and another one. And the question is, how can we leverage this for a hypothesis test? The error of first kind, as discussed before, is wrongly assuming a non-unique population descriptor, and then maybe, for example, going ahead with a t-test, although the underlying assumptions aren't satisfied. So the null hypothesis here is that the number of population descriptors is 2 or higher, and the alternative is that the population descriptor is unique. And the basic idea for the test is if sufficiently many bootstrap descriptors are in another cluster than the sample descriptor, then we do not reject, because we cannot rule out non-unique population descriptor. So this raises two questions. First, how to determine clusters of the bootstrap descriptors. Here we need a method with asymptotic uniform size and power results, which most clustering methods do not provide. And secondly, what are sufficiently many bootstrap descriptors in a different clusters? And for that, we need an asymptotic size result for the test statistic. So first, about determining clusters. To reliably identify clusters, we only consider the distances between the bootstrap descriptors and the sample descriptor. And if we have a one-dimensional descriptor space, the cluster containing the sample descriptor itself will only be represented by a falling slope, and then other clusters will have a rising and falling slope. Whereas for higher dimensions, the cluster containing the sample descriptor itself will start with a rising slope due to the spherical volume element. So what we want to find is the next rising slope after the first falling slope, because the first falling slope is that of the cluster containing the sample descriptor itself. And the onset of this rising slope is then the point after which we count all the bootstrap descriptors And this number is what's used in the test then. We use the multi-scale method for slope detection by Dümken and Walter because this has very nice size and power guarantees. Now, secondly, from asymptotic theory, we know that we have a unique descriptor if less than alpha half times b of the bootstrap descriptors are in another cluster than a sample descriptor. So if we want a test level of 5%, we need less than 2.5% of the points in another cluster than the sample descriptor for the test to reject. Okay, so to recap, the null hypothesis of the test is that there are non-unique population descriptors, whereas the alternative is that the population descriptor is unique. And the test statistic is defined as 2 over the number of bootstrap samples times the number of bootstrap samples after the onset of the rising slope after the first falling slope. And we reject if this value t is smaller than our test level alpha. And since t is crafted in such a way that it's essentially a p-value, we define the p-value as the minimum of 1 and t. Now let's look at 2 typical applications. One is the Fréchet mean on a manifold, which is very close to the motivating examples. We look at the female sea turtles data sets where the compass directions of these turtles are recorded leaving the beach after laying eggs. And we see that most of the turtles here move east-northeast to the seashore, but there is a second mode of turtles moving inland, almost in the exact opposite direction. And this is very similar to the example we looked at in the beginning, and it turns out there are actually several clusters of bootstrap descriptors as are visible in this histogram here, and the test does not reject with a p-value of around 0.8. This means the mean may be non-unique in this situation, as we might have already expected from the mode structure. The second application is in Centroid clustering, where we look at the classical iris data set, where 4 blossom features are measured for 3 species of iris. And the data set contains 50 iris blossoms for each species, so the sample size is 150, and the dimension of the descriptor space is 4. We look only at the first 2 principal components, so we can have nice 2-dimensional graphs which capture most of the variation here. And we see that one of the species is very distinct from the other 2, where the other 2 clusters are very close by, but they don't overlap very strongly, so there might be a chance to separate them. And if we do Gaussian mixture clustering, the cluster centers here are the stars, and each of the points is colored in the corresponding to the cluster center for which it has the highest likelihood. And it turns out we reproduce the species labels quite well. However, our test gives a p-value of p equal to 1. And this is because in some of the bootstrap samples, the upper points of the gray cluster are counted towards the black cluster, and the lower points of the black cluster are counted towards the gray cluster. And this gives one alternate clustering results. So there are several clusters of clustering results, and the test does not reject. So these clustering results are not reliable in this sense. If we take only 2 components, our test gives a p-value of 0. So it does clearly reject. So our cluster result is unique. And what happens then is that the blue cluster is always found as one cluster, and the gray and black is found as the other one. And there is no mixing between them. So in this sense, our hypothesis test here can be seen as a model selection criterion. But in contrast to typical model selection criteria, it does not simply prefer the model that best fits the data, but it evaluates how reliable a model is in fitting a data or in getting a fitting result. Yes, and that's all I wanted to talk about. Thank you very much.